Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the model serving platform, the infrastructure that takes trained machine learning models and serves predictions at scale with low latency, high throughput, and production-grade reliability. We'll cover how companies like Google, Netflix, and Uber deploy thousands of models behind APIs handling millions of inference requests per second. Whether you're preparing for a senior engineering interview or building ML infrastructure at scale, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the model serving platform, the infrastructure that takes trained machine learning models and serves predictions at scale with low latency, high throughput, and production-grade reliability. If you have ever wondered how companies like Google, Netflix, Uber, or OpenAI deploy thousands of models behind APIs that handle millions of inference requests per second, this video is for you. We'll walk through the functional requirements, non-functional requirements, system architecture, end-to-end user journey, core models, low-level design, and the trade-offs that come up in a senior system design interview. Whether you are preparing for a FANG interview or building ML infrastructure, let's get into it. Here is the core problem. A company has dozens of data science teams shipping hundreds of models, recommendation engines, fraud detectors, search rankers, large language models, and computer vision classifiers. Each model has different framework requirements: TensorFlow, PyTorch, XGBoost, ONNX. Each has different hardware needs. Some require GPUs, some run fine on CPUs, some need specialized accelerators. Deploying a model today requires a custom Docker image, manual Kubernetes configuration, hand-rolled autoscaling, and bespoke monitoring. There is no standardized way to do canary deployments, A/B testing, or shadow mode evaluation. When a model misbehaves in production, there is no quick rollback. Latency spikes go undetected until users complain. The business needs a unified model serving platform that abstracts away infrastructure complexity, standardizes deployment, and gives ML engineers a self-service path from trained model artifact to production endpoint with full observability. Let's walk through the functional requirements. First, the platform must support multi-framework model registration. Teams upload model artifacts in TensorFlow Saved Model, PyTorch TorchScript, ONNX, XGBoost, or custom container formats, and the platform handles packaging. Second, it must provide one-click deployment to a scalable serving endpoint with configurable hardware, CPU, GPU type, memory, and replica count. Third, it must support advanced traffic management including canary rollouts, A/B testing between model versions, shadow mode where a new model receives live traffic, but its predictions are logged and not served, and instant rollback to a previous version. Fourth, it must expose a unified prediction API with both synchronous real-time inference and asynchronous batch inference modes. Fifth, it must provide full observability, per model latency percentiles, throughput, error rates, prediction drift detection, and resource utilization dashboards with alerting. Now the non-functional requirements. Latency must be low. P50 under 10 milliseconds and P99 under 50 milliseconds for real-time inference endpoints. Throughput must scale to millions of predictions per second across the platform. Availability must be 99.99% because downstream services depend on model predictions for every user request. The platform must support horizontal autoscaling based on request rate, GPU utilization, and queue depth. It must be cost-efficient. Scale to zero for infrequently used models and bin-pack GPU workloads to maximize utilization. Model deployment must be fast. Under 5 minutes from artifact upload to live endpoint. The system must be secure with model access control, encrypted inference payloads, and audit logging. And it must be multi-tenant. Hundreds of teams sharing the platform without noisy neighbor interference. Here is the high-level system architecture. On the left, ML engineers interact with a model registry where they upload trained artifacts, register metadata, and define serving configurations. The deployment controller takes a serving configuration and orchestrates the infrastructure. It provisions compute via a resource manager, pulls model artifacts from object storage, and spins up inference servers using a runtime like Triton, TorchServe, or TensorFlow serving inside containers on Kubernetes. A traffic router sits in front of all inference servers and handles request routing, canary splits, AB assignments, and shadow duplication. An autoscaler monitors request queues and GPU utilization, scaling replicas up or down. A prediction cache stores frequently requested predictions to reduce redundant computation. An observability pipeline collects latency, throughput, error, and drift metrics, feeding dashboards and alerting systems. The key metrics to memorize: cold, P50 and P99 inference latency, measured end-to-end from API gateway to response. Throughput in predictions per second per model and platform-wide. GPU utilization percentage, which directly maps to cost efficiency. Model load time, the seconds from cold start to serving the first prediction. Error rate, the fraction of inference requests that fail or timeout. Prediction drift score, a statistical measure of how much the model's output distribution has shifted from its training distribution. Cache hit ratio for the prediction cache, which reduces GPU load. And deployment frequency, how many model versions are deployed per day across all teams. These metrics are what the business actually cares about. Let's trace the end-to-end user journey. An ML engineer at an e-commerce company finishes training a new product recommendation model. She uploads the PyTorch TorchScript artifact to the model registry and specifies serving requirements. 2 GPU replicas, max batch size of 32, P99 latency target of 30 milliseconds. She clicks deploy and the platform provisions GPU instances, loads the model, and runs a health check. She configures a canary rollout. 10% of traffic goes to the new model, 90% stays on the current version. The platform routes traffic accordingly, and she monitors the canary dashboard. After confirming the new model improves click-through rate by 4% with no latency regression, she promotes it to 100%. The old version stays registered for instant rollback if needed. The core models and algorithms. The model registry stores artifact metadata, version history, framework type, input and output schemas, and lineage. The inference server is the runtime that loads a model into memory, performs batching, and executes forward passes on hardware accelerators. Dynamic batching groups incoming requests into batches to maximize GPU throughput while respecting latency SLAs. The traffic router implements weighted routing using consistent hashing for A, B assignments, and mirroring for shadow mode. The autoscaler uses a control loop. It reads metrics like queue depth, GPU utilization, and request rate, computes a desired replica count using a target-based policy or predictive scaling, and issues scale commands. The prediction cache uses a content-addressable store keyed on model version plus input hash, with TTL-based eviction. The key trade-off is latency versus throughput. Larger batches improve GPU utilization, but increase tail latency for individual requests. Now the low-level design deep dive. The inference pipeline starts at the API gateway, which authenticates the request, looks up the model endpoint, and forwards to the traffic router. The traffic router checks canary and A, B configuration stored in a distributed config store, determines which model version to route to, and optionally duplicates the request for shadow mode. The request arrives at an inference server pod running on Kubernetes. The server's batcher queues the request until the batch window expires or the batch is full, then executes a forward pass on the GPU. Results are returned through the gateway. For batch inference, requests are submitted to a job queue, processed by a pool of workers, and results are written to object storage. The autoscaler runs a reconciliation loop every 15 seconds. It fetches metrics from Prometheus, computes desired replicas using the formula max of CPU target, GPU target, and queue depth target, applies smoothing to avoid flapping, and patches the Kubernetes HPA. Model artifacts are stored in S3 with versioning, pulled by an init container on pod startup, and cached on local NVMe for fast restarts. Key takeaways for your interview. First, a model serving platform is fundamentally a request routing and compute orchestration system, So emphasize traffic management, autoscaling, and resource scheduling. Second, dynamic batching is the single most important optimization for GPU inference. Explain the trade-off between batch size, latency, and throughput clearly. Third, canary deployments, A/B testing, and shadow mode are critical for safe model rollouts in production, so describe how the traffic router implements each pattern. Fourth, the autoscaler must balance cost efficiency with latency SLAs, and predictive scaling based on historical patterns outperforms reactive scaling alone. Fifth, observability and drift detection close the feedback loop. Without them, you cannot know if a deployed model is degrading silently. If you can walk through this system with these 5 points, you will signal strong senior-level design thinking. That's it for the model serving platform. If this helped, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on the model serving platform. We covered the full picture, from model registry and deployment controller, through inference servers, dynamic batching, traffic routing, autoscaling, prediction caching, and the low-level design of the inference pipeline. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.